So our first section this week is section 6.2, area between two curves. Want to make a reminder that we know how to find the area of a region bounded between A and B of a function. If I wanted to define that area, all I would do is I would take the definite integral between A and B of f of x dx. And we have all of our rules for finding these antiderivatives or definite integrals. Okay? What I want to do is, let's say I had f of x there, and I had a second function g of x. And instead of finding the area just underneath f of x or underneath g of x, I wanted to find the area that's in between f of x and g of x, and not the area underneath g of x. So if I'm looking at it, well, one way you can think about it, hey, I can take the purple area, f of x, and then subtract the area of g of x. So that would be minus the integral from a to b of g of x dx. Well, one thing we need to look at is here I drew both curves so that both curves are always above the x-axis, and always one curve is above the second curve. So there's two other things we need to consider. What happens if one or both curves falls below the x-axis? And what happens if they change which curve is the top curve and which curve is the bottom curve? So the first thing we need to take into account, let's just say f of x, again my purple graph, is always above. And then I have my g of x curve, and that it sometimes goes down below. Okay, and I'm going to do a region from A to B. And I want the area bounded between these two curves. Well, one thing you should know that you're able to do to any curve is that if you add a constant to it, all that does is it moves the curve up. And remember, this says to take any antiderivative. Okay? So remember that if I was doing the indefinite integral, I would have a plus c. Well, I can add the same plus c to both of these, and it would move both of my curves up. So what I'm going to do is just pick an arbitrary c that I can add to both of these. That's going to move both of these curves up above. So both of them are above the x-axis. So let's say that this number right here, I'm going to call u. So I could end up with the graph. I'm going to take my g of x graph and raise it u. This would be g of x plus u. And then I would have f of x plus u. And if I bound it between the same region, and again, these are supposed to be the same shape graphs, notice I can now use the above formula. Well, look what happens here is that up here I'm going to have a plus u, and then I'm going to have a plus u here that's going to be subtracted, and u minus u cancels, becomes 0. So I can still use the same original formula if my one or both of my curves drops below the x-axis. I can find the region between the two curves by taking the integral of the top curve minus the integral of the bottom curve. So the other point we want to take into account is what happens if one curve is not always the top curve. Okay, so let's draw an example here. Again, my purple will be the f of x curve. Then I'm going to use my blue for my g of x curve. And let's say I want to find the area between the curves from A to B. That means I want to find that area, and that area. So if I wanted to find the areas of this, what I would do is I would end up breaking it down. I'm going to call this U and V. I would break it down into 3 regions. So my final answer would be the integral for the first region, plus the integral for the second region, plus the integral for the third region. So in this case, let me label my g of x. And the way I remember this, it's the integral of the top minus the integral of the bottom. Or we're going to see that we can rotate and take in, if it's easier to integrate off of y versus x, we would take the integral of the right-hand side minus the integral of the left-hand side. I'll show you a picture of that in a minute. So what I do is break this down into 3 integrals, 3 sets of integrals that I'm going to add together. Well, it's the integral of the top minus the integral of the bottom. So the top is f, the bottom is g. So the integral from a to u of f of x dx minus the integral from a to u of g of x dx. So that's the first region. Then the second region, g is on top. So it would be the integral from u to v of g of x dx minus the integral from u to v of f of x dx. And my final region, f again, is on top. So it is the integral from v to b of f of x dx minus the integral from v to b of g of x dx. So if you switch which curve is on top, you will also switch, you'll actually have to have a new integral for each one of those different sections. Okay, and the last thing I talked about is it's sometimes easier to do my integral from across y's. So easier to integrate with respect to y. So I'm going to draw you a couple graphs just so I can show you. Sometimes that it is easier. So I am going to draw you 2 functions. The first function is, we'll do this one, and that is y equals x to the 2/3. And the second function I'm going to draw is y equals x minus 4. And actually that should be a 45-degree angle, so let me draw it a little better. And if I wanted to know the area of the region between here, we're going to call it 0. So A is equal to 0. And B, well, B is when those 2 things intersect, and that would be at the point 8, 4. I could do this integral 2 different ways. Well, I can do the top curve minus the bottom curve. But here, notice the bottom curve between this region and this region, where I'm going to write u equals 4. The bottom curve is the equation x equals 0. And then my bottom curve shifts. So you can see if I'm doing it with relationship to x, I'm going to have to do 2 separate integrals. So look what happens if I rearrange these 2 equations. I can write this as x equals y plus 4. I can raise both sides to the 3/2 powers, and I can get x equals y to the 3/2. And then, if I look at the graph from here, what I would do is I would then take the blue curve minus the purple curve, and notice that if I'm looking at it from this side, the blue curve is always on top. And here, the purple curve is always on the bottom, so I'd be able to get away with a single integral. There is nothing wrong with doing it split into two different integrals, but something like this, it would be probably quicker to do it as a single integral. So, again, that's how we're going to find the area between two curves. We're either going to take the integral of the top function minus the integral of the bottom function, or we're going to take the integral of the right function minus the integral of the left function. Notice from here, let me just write out what I would do here. If I'm doing it with respect to y, it would be the integral of the blue curve, which is y plus 4 dy, minus the integral of the purple curve, which is y to the 3/2 dy, going from y equals 0 to y equals 4. And then I would do the integration on this, and I'd be able to solve and find the area in between the two regions. And I'm going to do some of these for examples.